So here's something to think about as you settle in tonight. Right now, at this exact moment, you are moving through space at roughly 67,000 miles per hour. That's the speed of the Earth in its orbit around the Sun. You don't feel it. There's no wind in your hair, no rumble beneath you, nothing at all to suggest that you are hurtling through the void at a speed that would carry you from New York to Los Angeles in about 2.5 minutes. And on top of that orbital speed, the entire solar system, the Sun, the Earth, all 8 planets, all their moons, every asteroid and comet and grain of dust, the whole thing is moving through the Milky Way galaxy at about 490,000 miles per hour. And the galaxy itself is moving through the universe at something like 1.3 million miles per hour relative to the cosmic microwave background. You are stacked on a tower of motions, each one faster and more dizzying than the last, and you feel absolutely none of it. You're just lying there, breathing. Maybe your eyes are closed, and the universe is carrying you along at a combined speed that would boggle the mind if you let it. But the pillow still feels soft, and the room is still quiet. And that's kind of the perfect starting point for what we're going to talk about tonight. The solar system, the whole thing, from the sun at the center to the frozen, dark edges where the influence of our star finally, grudgingly, fades away. We're going to take our time with it, the way you'd take your time walking through a place you've always wanted to visit. There's no rush. Some of this you'll know already, and that's fine. Sometimes familiar things are the best things to hear when you're settling down, like hearing a song you already love. And some of it might surprise you, because the solar system is stranger, more violent, more beautiful, and more improbable than most people realize. We've been staring up at it for as long as there have been people to stare, and we're still figuring it out. Let's start where every story about the sky starts, which is with people looking up. And people have been looking up for a very, very long time. We have evidence that ancient humans tracked the movements of the moon and the sun at least as far back as 30,000 years ago. There are carved bones and painted cave walls that seem to record lunar phases, tally marks that line up with the moon's 29.5-day cycle from new to full and back again. We don't know exactly what those ancient observers were thinking. Maybe they were tracking time, or planning hunts, or marking the rhythms of the natural world they depended on. But they were paying attention. They noticed that the sky wasn't random. It had patterns, and the most obvious pattern, the one you'd notice if you spent even a few nights paying attention, is that the stars move together. The whole sky rotates, slowly and majestically, as if all the stars were painted on the inside of a giant dome that spins overhead once a day. The constellations hold their shapes. Orion always looks like Orion. The Big Dipper is always a dipper. From night to night, from month to month, the stars are remarkably fixed relative to each other. The ancient Greeks called them the fixed stars, and they imagined them literally attached to a crystalline sphere that rotated around the Earth. But here's the thing. Not everything in the sky behaves that way. If you watch carefully, over weeks and months, you'll notice that a handful of bright objects don't stay put. They move. They wander among the fixed stars, drifting slowly from constellation to constellation, sometimes speeding up, sometimes slowing down, sometimes, and this is the really puzzling part, appearing to stop, reverse direction, and go backwards for a while before resuming their forward motion. The Greeks had a word for these objects. They called them planetes, which means wanderers, and that's where our word planet comes from. These wandering stars, these planets, were Mercury, Venus, Mars, Jupiter, and Saturn, the 5 that are visible to the naked eye. Together with the sun and the moon, they made 7 moving objects in the sky, and it's not a coincidence that we have 7 days in the week. Sunday for the sun, Monday for the moon, Saturday for Saturn. The other connections are more obvious in French or Spanish or Italian, where Tuesday is Mardi or Martes, Mars's day, and so on through the week. So for thousands of years, humans watched these 7 wanderers move across the sky and tried to make sense of what they were seeing. And the explanation that held sway the longest, the one that dominated Western astronomy for something like 1400 years, came from a Greek mathematician and astronomer named Claudius Ptolemy, working in Alexandria, Egypt, around 150 CE. Ptolemy's model put the Earth at the center of everything. The sun, the moon, and all the planets orbited around a stationary Earth, each on its own sphere, nested inside each other like Russian dolls. It was an elegant idea, and it matched the most obvious evidence of your senses. After all, the ground beneath you certainly feels like it's standing still, and the sky certainly looks like it's revolving around you. But there was that nagging problem of retrograde motion, the way Mars and the other outer planets sometimes seem to reverse direction and loop backwards through the stars. If the planets were simply circling the Earth on perfect spheres, they should move in one direction only. So Ptolemy introduced something ingenious but complicated. He said that each planet doesn't just orbit the Earth on a big circle, it also moves on a smaller circle, called an epicycle, that rides on the big circle, like a ball rolling along the rim of a spinning wheel. And by choosing the right sizes and speeds for these circles within circles, Ptolemy could make his model match the observed motions of the planets with remarkable accuracy. Need more accuracy? Add another epicycle, and maybe another. The system grew complex, with circles upon circles upon circles. But it worked well enough to predict eclipses and planetary positions, and it made intuitive sense to a world that believed the Earth was the center of creation. And so the Ptolemaic system endured for over 1,000 years. Through the fall of Rome, through the rise of Islam, through the medieval period in Europe, through the preservation and translation of ancient texts by Arab scholars who refined and improved the model, Ptolemy's geocentric universe was the accepted picture of reality. It wasn't just a scientific model, it was woven into philosophy, theology, and the very fabric of how people understood their place in the cosmos. The Earth was the center. Humans were the point of it all. The heavens revolved around us. And then, in the early 1500s, a quiet, cautious, deeply religious Polish astronomer started pulling on a thread that would unravel the whole thing. Nicolaus Copernicus was born in 1473 in Royal Prussia, in a town called Torun, on the banks of the Vistula River. He was raised by his uncle, a Catholic bishop, after his father died when Nicolaus was about 10. He studied at the University of Krakow, then traveled to Italy, to Bologna, Padua, and Ferrara, where he studied law, medicine, and astronomy. He was, by all accounts, a careful and somewhat private person. He served as a canon in the Catholic Church, practiced medicine, helped manage the diocese's finances, and somehow, alongside all of that, worked on a radical new model of the cosmos that he spent most of his adult life refining, but was deeply reluctant to publish. Here's what Copernicus figured out, and it's one of those ideas that sounds simple, but shook the world to its foundations. He said, "What if the Earth isn't at the center? What if the sun is at the center, and the Earth, along with all the other planets, orbits around the sun?" This is the heliocentric model, helio from the Greek for sun, and the beautiful thing about it is that it explained retrograde motion naturally, without any epicycles. Think about why. Mars orbits the sun farther out than Earth does, and it moves more slowly. So every couple of years, the faster-moving Earth catches up to Mars, and passes it on the inside track, like a car overtaking a slower car on a highway. And when that happens, from our perspective, Mars appears to slow down, stop, and move backwards against the background stars, just for a few weeks, before it appears to resume its forward motion. It's an illusion caused by our own changing vantage point. You've experienced this same illusion on the highway. You're passing a slower car, and for a moment, that car seems to drift backwards relative to the distant mountains, even though it's still moving forward. Retrograde motion, explained. No epicycles needed. Copernicus wrote up his heliocentric model in a massive work called De Revolutionibus Orbium Coelestium, on the revolutions of the celestial spheres, and he hesitated for years about publishing it. He circulated a summary of his ideas privately in a short manuscript called the Commentariolus around 1514, but the full book didn't appear until 1543, the year he died. According to legend, a copy of the published book was placed in his hands on his deathbed, and he may have seen it just before he passed. It's a poignant image, this cautious, private man who spent his life working on an idea that would change everything, finally seeing it in print just as he left the world. Now, Copernicus's model was a conceptual revolution, but it wasn't perfect. He still insisted on circular orbits, because circles were considered the most perfect geometric shape, and he assumed that celestial motions must be built from perfect circles. But orbits aren't actually circles. They're ellipses, slightly squished circles, like an oval. And it took two more extraordinary figures to get from Copernicus's circular heliocentric model to the true picture of how planets actually move. One of them was a flamboyant, big-living Danish nobleman. The other was a quiet, myopic, deeply mathematical German who would become his assistant, inherit his data, and use it to crack the code of planetary motion. Their story is one of the strangest and most fruitful collaborations in the history of science. And let me tell you about Galileo's moment with the telescope, because it's one of those stories that never gets old, no matter how many times you hear it. In 1609, Galileo Galilei, a mathematics professor at the University of Padua in Italy, heard about a new invention from the Netherlands, a device using two lenses in a tube that could make distant objects appear closer. A spyglass, people called it. Galileo didn't invent the telescope, but he improved it dramatically, grinding his own lenses to achieve magnifications of around 20 times. And then he did something that changed everything. He pointed it at the sky. What he saw, night after night through the winter of 1609 and into 1610, was staggering. The moon wasn't a perfect, smooth sphere as Aristotle had taught. It was rough, mountainous, pockmarked with craters. It had terrain. It looked like Earth. He pointed his telescope at the Milky Way and discovered that the faint, luminous band across the sky was actually composed of countless individual stars, too faint and too numerous to see with the naked eye. He observed Venus and found that it showed phases, like the moon's phases, which could only be explained if Venus orbited the Sun, not the Earth. That was a direct hit against the Ptolemaic model. And on the night of January 7, 1610, he pointed his telescope at Jupiter and noticed 3 tiny stars in a line near the planet. Over the following nights, he watched them change position. A 4th appeared. They weren't stars. They were moons, orbiting Jupiter. Galileo published his findings in a small book called Sidereus Nuncius, the Starry Messenger, in March 1610, and it caused a sensation across Europe. The implications were enormous. If Jupiter had its own moons, then not everything orbited the Earth. The geocentric model had claimed that Earth was the center of all celestial motion, and here were 4 objects clearly circling something else. It didn't prove the heliocentric model by itself, but it demolished one of the key arguments against it, the argument that the Earth must be the center because everything revolves around it. Galileo, characteristically bold and occasionally reckless, became an outspoken advocate for Copernicus's heliocentric model, which eventually brought him into conflict with the Catholic Church. In 1633, he was tried by the Inquisition, forced to recant his support for heliocentrism, and spent the last 9 years of his life under house arrest. But the evidence was out there. The observations were reproducible, and the geocentric model was living on borrowed time. Within a generation, educated Europeans had largely abandoned it. Tycho Brahe, and people argue about how to pronounce his name, but Tycho is the part everyone agrees on, was born in 1546 into Danish nobility. He was essentially kidnapped as an infant by his wealthy uncle, who raised him and paid for his education, which is a whole story in itself. Tycho was brilliant, combative, extravagant, and deeply committed to the idea that astronomy needed better data. He lost part of his nose in a sword duel as a young man. Some accounts say it was over a mathematical disagreement, which is the most astronomer thing I've ever heard, and for the rest of his life he wore a prosthetic nose, reportedly made of brass or copper, though there are claims it might have been gold or silver for special occasions. When his grave was opened in 2010, researchers found traces of copper and zinc on his skull, suggesting the everyday prosthetic was indeed brass. But the really important thing about Tycho was this: he built the best astronomical observatory in the world. On the island of Haven, given to him by the King of Denmark, Tycho constructed a facility called Uraniborg, the Castle of the Heavens, and later a second observatory called Stjerneborg. For over 20 years, from roughly 1576 to 1597, Tycho and his assistants made meticulous, incredibly precise observations of the positions of stars and planets. No telescopes. The telescope wouldn't be invented for another decade. Just beautifully engineered sighting instruments, large metal quadrants and armillary spheres, and an obsessive attention to accuracy. Tycho's measurements were accurate to about 1 arcminute, which is 1/60th of a degree. That might not sound impressive, but it was 5 to 10 times better than anyone had achieved before, and it was that improvement in precision that made all the difference, because Tycho himself couldn't quite figure out what the data was telling him. He rejected Ptolemy's geocentric model, but he also couldn't bring himself to accept Copernicus's heliocentric one, partly for astronomical reasons, partly for physical ones. He couldn't understand why, if the Earth were really moving, you couldn't feel it or detect it, and partly, perhaps, for theological ones. So he proposed his own compromise, the Tychonic system, in which the Sun and Moon orbit the Earth, but all the other planets orbit the Sun. It was mathematically equivalent to Copernicus's model in terms of predictions, but it kept the Earth fixed. History would leave it behind. What history would not leave behind was Tycho's data, because in the last years of his life, after a falling out with the new Danish king and the loss of his beloved fen, Tycho moved to Prague, to the court of Emperor Rudolf II, and there he hired a young German mathematician as his assistant. That mathematician was Johannes Kepler, and the relationship between these two men, the boisterous, wealthy, prosthetic-nosed observer and the impoverished, half-blind, mathematically obsessed theorist, is one of the great odd couple stories in science. Kepler was born in 1571 in the town of Weil-der-Stadt, in what is now southwestern Germany. His childhood was difficult. His father was a mercenary who disappeared when Kepler was young. His mother was later accused of witchcraft. He spent years defending her in court, and he suffered from poor health and weak eyesight his entire life. But his mathematical ability was extraordinary. almost preternatural, and he was driven by a deep, almost mystical conviction that the universe was built on mathematical harmony, that God had designed the cosmos according to geometric principles, and that it was the job of the astronomer to discover those principles. When Tycho died suddenly in 1601, possibly from a bladder infection aggravated by his refusal to excuse himself from a banquet, which is, again, an incredibly Tycho way to go, Kepler inherited his position as imperial mathematician and, crucially, gained access to Tycho's treasure trove of observational data. And Kepler proceeded to do something remarkable with it. He spent years, trying to figure out the orbit of Mars. He tried circles, he tried combinations of circles, he tried every trick he could think of, and nothing worked. Nothing fit Tycho's data, which was too precise to fudge. And finally, reluctantly, because he loved circles as much as anyone, Kepler tried a different shape, an ellipse, and it fit perfectly. That was the first of Kepler's 3 laws of planetary motion, published in 1609 in a book called Astronomia Nova. Planets orbit the Sun not in circles, but in ellipses, with the Sun at one focus of the ellipse. The second law, published in the same book, described how a planet's speed varies in its orbit. It moves faster when it's closer to the Sun and slower when it's farther away, sweeping out equal areas in equal times. And the third law, published in 1619, established a precise mathematical relationship between a planet's orbital period and its average distance from the Sun. The square of the period is proportional to the cube of the distance. These 3 laws were revolutionary. They described how planets actually move with stunning accuracy, and they did it with simple, elegant mathematics. No epicycles, no equants, no circles within circles, just ellipses, areas, and a clean ratio. But here's the thing that nagged at Kepler, and that nagged at everyone who came after him for the next 70 years. His laws described what the planets do, but they didn't explain why. Why do planets move in ellipses? Why do they speed up when they're closer to the Sun? What force is acting on them, and how does it work? Kepler himself had some intuitions. He suspected some kind of force emanating from the Sun, something pushing or pulling the planets along, but he couldn't make it rigorous. The math wasn't there yet, the physics wasn't there yet, and this is where the story arrives, at one of the most famous figures in all of human history, a person whose name has become almost synonymous with genius, Isaac Newton. Born on Christmas Day, 1642, in Woolsthorpe, Lincolnshire, England, though if you use the old Julian calendar, which England was still on at the time, the date was actually January 4th, 1643, by the Gregorian calendar that most of the rest of Europe had already adopted. Newton's early life was not easy. His father died before he was born. His mother remarried and left young Isaac with his grandmother. He was, by most accounts, a solitary, intense, sometimes difficult child who showed early signs of extraordinary intellectual ability, but also a capacity for grudges and bitter disputes that would follow him his entire life. Newton went to Trinity College, Cambridge, in 1661, and during the years 1665 and 1666, when the university was closed due to the Great Plague, he retreated to his family home in Woolsthorpe and went on what might be the most productive intellectual bender in history. During those plague years, working largely in isolation, Newton developed his theory of calculus, his theory of optics and the nature of light, and the beginnings of his theory of universal gravitation. 3 of the most important contributions to science ever made, all from one person, all in roughly 18 months. The famous story of the apple falling on his head is almost certainly not literally true. But Newton himself later said that seeing an apple fall in the garden did set him thinking about whether the same force that pulled the apple toward the Earth could extend all the way to the Moon, holding it in its orbit. The question was, does the force that makes things fall on Earth also govern the motions of the heavens? And the answer, as Newton worked it out over the following 2 decades, he didn't actually publish his masterwork, the Principia Mathematica, until 1687, partly because he was a perfectionist and partly because he was busy with other things, including alchemy and biblical chronology. The answer was yes. The same force, gravity, a single, universal force that acts between every pair of objects in the universe, pulling them toward each other, with a strength proportional to the product of their masses and inversely proportional to the square of the distance between them. That inverse square law is the key. Double the distance, and the force drops to 1/4. Triple the distance, force drops to 1/9. It fades with distance, but it never quite reaches 0. The sun pulls on the Earth, and the Earth pulls on the sun. The Earth pulls on the Moon, and the Moon pulls on the Earth. That's what makes the tides. Jupiter pulls on its moons, and its moons pull on Jupiter. Everything pulls on everything else, across the entire universe. And here's what's really beautiful. Newton showed, mathematically, that if you start with this one simple law of gravitational force and combine it with his laws of motion, you can derive Kepler's 3 laws of planetary motion. All 3 of them fall out of the math as consequences. Elliptical orbits? That's what you get when one object is bound gravitationally to another. The equal areas law? That's a consequence of the conservation of angular momentum under a central force. The relationship between period and distance? It drops right out of the inverse square law applied to circular and elliptical orbits. Kepler's laws weren't just descriptions anymore. They were explained. They were unified. One force, one set of equations, and suddenly the entire motion of the solar system made sense. Think about what an achievement that is. For thousands of years, the motions of the planets had been mysterious, seemingly arbitrary, governed by invisible rules that nobody could fathom. And Newton said, "It's gravity. The same thing that makes your coffee mug fall off the table is the thing that holds the solar system together." The same physics operates everywhere, at every scale, from the apple to the moon to the most distant planet. That's the universality in universal gravitation. It was one of the most profound unifications in the history of human thought. Now, I want to take a small detour here, because we've talked about Kepler's laws and Newton's gravity, and there's a detail in this story that often gets skipped, and it's too good to skip. Remember how I mentioned that Newton needed a push from Edmund Halley to publish the Principia? Halley's role in the history of the solar system is actually much bigger than that. Edmund Halley, born in 1656, the son of a wealthy soap maker in London, was a brilliant astronomer in his own right. He catalogued stars in the southern hemisphere from the island of St. Helena in the South Atlantic. He studied trade winds and magnetic variation, but his most famous contribution, the one that bears his name to this day, came from applying Newton's gravitational theory to comets. Before Halley, comets were thought to be one-time visitors. They would blaze across the sky and disappear, never to return. But Halley noticed something. Looking back through historical records, he found that a bright comet had appeared in 1531, and again in 1607, and again in 1682. The intervals were about 75 to 76 years. Could they be the same comet, returning again and again on an elongated elliptical orbit? Using Newton's equations, Halley calculated the orbit and predicted that the comet would return around 1758. He knew he wouldn't live to see it. He was already in his 70s when he made the prediction, and he asked that if the comet did return, people would acknowledge that it was an Englishman who had predicted it. Halley died in 1742. On Christmas Day, 1758, a German farmer and amateur astronomer named Johann Georg Pallich spotted the comet exactly where Halley's calculations said it would be. It was a triumph of Newtonian physics, a proof that gravity governs not just planets but comets too. And the comet has been called Halley's Comet ever since. It last visited the inner solar system in 1986, and it'll be back around 2061. If you're young enough, you might see it. The discovery of Halley's Comet as a periodic visitor also changed how people thought about the solar system. It wasn't just planets and moons following tidy orbits. There were these wild cards, icy visitors plunging in from the outer darkness on elongated paths, swinging around the sun and racing back out again. The solar system had more variety, more dynamism, more chaos than the neat clockwork model suggested. And that realization would only deepen as astronomers discovered more and more about what's out there. And with Newton's gravity in hand, astronomers could finally do something they'd never been able to do before. They could predict. Not just describe the motions of the planets, actually predict where a planet would be in 10 years, or 100 years, or 1,000. They could calculate the exact timing of eclipses. They could determine the mass of the sun, the masses of the planets, the shapes and sizes of orbits, all from the comfort of a desk with a pen and paper and Newton's equations. The solar system had become a clockwork, a magnificent machine running on mathematical laws, and for the first time in history, humans could read the clock. And Newtonian gravity did something else, something that still gives me chills when I think about it. It predicted the existence of a planet that nobody had ever seen. By the 1840s, astronomers had noticed that Uranus, discovered in 1781 by William Herschel, which we'll come back to, wasn't quite following the orbit that Newton's equations predicted. It was being pulled slightly off course, tugged by the gravity of something unseen. Two mathematicians, Urbain Le Verrier in France and John Couch Adams in England, working independently, calculated where that unseen planet must be. Le Verrier sent his prediction to the Berlin Observatory, and on September 23, 1846, the astronomer Johann Galle pointed his telescope at the predicted position and found Neptune within 1 degree of where Le Verrier said it would be. A new planet, discovered not by looking through a telescope, but by solving equations. Gravity told us it was there before any eye had seen it. That is the power of understanding the physics. But to truly appreciate the solar system, you need to understand the thing at the center of it, the sun. And the sun is so much more extraordinary than most people realize. It's easy to take it for granted. It rises, it sets, it's bright, it's warm. But when you start to look at the numbers, at the sheer scale and violence and power of our star, it becomes genuinely staggering. Let's start with size. The sun is about 865,000 miles in diameter. That's about 109 times the diameter of Earth. If the Earth were a marble, the sun would be a ball about 15 feet across, roughly the height of a 2-story building. And volume? You could fit about 1.3 million Earths inside the sun. It contains 99.86% of all the mass in the entire solar system. Everything else, all the planets, all the moons, all the asteroids, all the comets, everything, adds up to less than 0.2%. The sun isn't just the center of the solar system. It is the solar system, with everything else being almost literally rounding errors. Now, what is the sun exactly? It's a ball of hot gas, mostly hydrogen, about 73% by mass, and helium, about 25%, with a smattering of heavier elements making up the remaining 2%. Those heavier elements, oxygen, carbon, iron, neon, and so on, are tiny by proportion, but the Sun is so massive that even that tiny fraction adds up to thousands of times the mass of Earth. The surface temperature is about 5,500 degrees Celsius, which is why it glows, a brilliant white yellow. But the surface is the cool part. Down in the core, where the real action happens, the temperature is about 15 million degrees Celsius, and the pressure is about 250 billion times the atmospheric pressure on Earth's surface. Under those conditions, something remarkable happens, something that powers not just the Sun, but every star you've ever seen in the night sky. Nuclear fusion. And here's how it works. Stripped down to the basics. The Sun's core is so hot and so dense that hydrogen atoms, or more precisely, the nuclei of hydrogen atoms, which are just single protons, are moving so fast and are packed so tightly together that they can overcome their mutual electromagnetic repulsion and actually collide and stick together. Fuse together. Because protons are all positively charged, and positive charges repel each other, and under normal circumstances, two protons will push each other away long before they get close enough to interact. But at 15 million degrees, the protons are moving fast enough that some of them slam together hard enough to get within range of the strong nuclear force, the force that binds protons and neutrons together inside atomic nuclei. The strong force is incredibly powerful, but it only operates over incredibly short distances, about the size of a proton itself. So you need to get the protons close enough for the strong force to grab them, and you need enormous temperature and pressure to make that happen. The specific process is called the proton-proton chain, and it takes several steps. First, two protons collide and fuse. One of them converts into a neutron through a process involving the weak nuclear force, and you get a deuterium nucleus, one proton and one neutron, plus a positron and a neutrino. Then the deuterium nucleus captures another proton to form helium-3, and then two helium-3 nuclei collide to form helium-4, regular helium, releasing two protons back into the mix. The net result is that four protons have been converted into one helium-4 nucleus, two positrons, two neutrinos, and, here's the important part, energy. A lot of energy. Where does the energy come from? This is where Einstein's most famous equation enters the story. E equals mc squared. The helium-4 nucleus has slightly less mass than the four protons that went into making it, about 0.7% less. That missing mass has been converted into energy, and because the speed of light squared is such an enormous number, even that tiny fraction of mass converts into a staggering amount of energy. Every second, the Sun converts about 4 million tons of matter into energy through fusion. 4 million tons just gone, every second. Vanished into photons and neutrinos. And it's been doing this for about 4.5 billion years, and it has enough hydrogen fuel left to continue for roughly another 5 billion years. The energy produced in the core doesn't escape immediately, though. Here's something wonderful. A photon created in the Sun's core, a packet of gamma-ray energy produced by fusion, doesn't shoot straight out to the surface. The core is so incredibly dense that the photon travels only a tiny fraction of a millimeter before it's absorbed by another atom, which then re-emits it in a random direction. Then it's absorbed again, re-emitted again. Over and over, in a random walk, bouncing this way and that through the dense interior. The Sun's core is about 1/4 of the way from the center to the surface, and it takes a photon somewhere between 10,000 and 170,000 years, estimates vary depending on assumptions, to random walk its way from the core to the surface. Let that sink in. The light that's warming your face on a sunny afternoon started its journey from the sun's core before the last ice age, before agriculture, before human civilization. It's been bouncing around inside the sun for all that time, slowly losing energy, gradually shifting from gamma rays to X-rays, to ultraviolet to visible light, and it finally emerged from the surface about 8 minutes ago, crossed the 93 million miles to Earth at the speed of light, and arrived at your skin, ancient and ordinary and miraculous all at once. And while we're talking about the sun, it's worth pausing on something that often gets glossed over, which is how the sun and the entire solar system actually formed in the first place. Because the story of the solar system's birth is really a story about gravity and gas and dust and the deep patience of physics. About 4.6 billion years ago, in this arm of the Milky Way galaxy, there was a cloud of gas and dust. A molecular cloud, astronomers call it, mostly hydrogen and helium, with traces of heavier elements that had been forged in earlier generations of stars and scattered across space when those stars exploded as supernovae. These clouds are enormous, light years across, and very cold and very thin by everyday standards, just a few thousand molecules per cubic centimeter in the dense parts. Compare that to the air you're breathing, which has about 25 billion molecules per cubic centimeter. Space, even in a dense cloud, is extraordinarily empty. But something disturbed this particular cloud. Maybe a shock wave from a nearby supernova. Maybe a ripple from the density wave of a spiral arm. Whatever it was, some region of the cloud got nudged a little denser, and that was enough to start a process that's as beautiful as it is inevitable. The denser region had more mass, so it had more gravity, so it pulled in more gas, which made it denser still, which increased the gravity further. A gravitational feedback loop. Collapse. Once it starts, it feeds itself. The cloud fragment began to contract, slowly at first, then faster, and here's a crucial piece of physics. The collapsing cloud had some very slight rotation. Almost everything in the universe is rotating a little, if only because of random turbulence. And as the cloud contracted, it spun faster, for the same reason an ice skater spins faster when they pull their arms in. Conservation of angular momentum. The shrinking cloud spun up, and because of that rotation, it didn't collapse into a sphere. Instead, it flattened. Material falling inward could easily move along the rotation axis, toward the equator, but the centrifugal effect of the spin prevented it from collapsing all the way in at the equator. So the cloud evolved into a flattened, spinning disk with a dense, hot lump at the center. That disk is called the protoplanetary disk, or sometimes the solar nebula. The dense lump at the center was the proto-sun, growing steadily as more material fell onto it. And this is why the solar system is flat. If you've ever seen a diagram of the solar system, all the planets orbiting in roughly the same plane, and wondered why it's not more of a random scatter, with planets going every which way, this is the answer. They all formed from the same flat disk, so they all orbit in roughly the same plane, and they all go around in the same direction, because they inherited the rotation of the original cloud. That flatness is a fossil, a memory of the disk that gave birth to everything. Now, inside that disk, the temperature wasn't uniform. Close to the proto-sun, where the disk was dense and being heated by the growing star's radiation, temperatures were very high, hundreds or even thousands of degrees. Only materials with very high melting points could exist as solids in that inner region. Metals, silicate minerals, rocky stuff. Farther out, beyond a boundary that scientists call the frost line or snow line, located at roughly the present-day orbit of Jupiter, temperatures dropped low enough for volatile compounds, water, ammonia, methane, to freeze into solid ice crystals. And that distinction between the hot inner disk and the cold outer disk is the fundamental reason the solar system has two very different kinds of planets. The rocky, dense inner planets, Mercury, Venus, Earth, Mars, formed from the refractory materials that could survive close to the Sun. The giant outer planets, Jupiter, Saturn, Uranus, Neptune, formed beyond the frost line, where the abundance of ice gave them much more solid material to start with, allowing them to grow large enough to gravitationally capture enormous envelopes of hydrogen and helium gas. But let's not get ahead of ourselves. The process of actually building a planet is something worth slowing down for, because it's one of those things that seems impossible when you first hear about it, and then gradually starts to make sense. It starts with dust grains, tiny, microscopic particles, smaller than grains of sand, floating in the protoplanetary disk. These grains collide with each other, gently, and sometimes they stick together, not through gravity. They're far too small for gravity to matter, but through electrostatic forces and van der Waals forces, the same gentle attractions that make dust cling to your furniture. Two grains stick together to make a slightly bigger grain. That bigger grain collides with another, and another. Slowly, over thousands of years, the grains build up into pebbles, then into rocks, then into boulders. This process is called accretion, and in the beginning, it's painfully slow. But as the clumps get bigger, things start to change. A rock-sized object has more surface area to sweep up other particles. A boulder-sized object has a little bit of gravitational pull, tiny but real, that helps attract more material. And once you get to something a few miles across, what astronomers call a planetesimal, gravity becomes the dominant force, and growth accelerates dramatically. Planetesimals attract each other, collide, merge, sometimes shatter and reform. It's a process of building and destroying and rebuilding, violent and chaotic, and over a few million years, which is actually remarkably fast on cosmic timescales, you end up with a handful of large bodies that have swept up most of the material in their orbital zones. These are the protoplanets, and they're the seeds of the planets we know today. And this brings us to the inner solar system, the zone of rock and metal and relentless heat, where the four terrestrial planets formed. And each one of them turned out so different from the others, so dramatically, bizarrely different, that it's one of the great puzzles and one of the great stories of planetary science. Four worlds, born from the same disk, orbiting the same star, and yet you could hardly imagine four more different places. Let's start closest to the Sun, Mercury, the runt of the planetary litter. It's the smallest planet in the solar system, about 3,000 miles in diameter, only a little larger than our Moon. It's so small and so close to the Sun that it was historically hard to study. It's always low in the sky, visible only briefly after sunset or before sunrise, lost in the sun's glare. For a long time, we knew very little about it, and then spacecraft went there, and what they found was a world of extremes and contradictions. Mercury has almost no atmosphere, just the thinnest wisp of atoms, sodium, oxygen, hydrogen, helium, blasted off the surface by the solar wind and by micrometeorite impacts, constantly escaping into space and constantly being replenished. Without an atmosphere to trap heat or distribute it, Mercury's surface experiences the most extreme temperature swings of any planet. On the sunlit side, temperatures soar to about 800 degrees Fahrenheit, hot enough to melt lead and zinc. On the night side, temperatures plummet to about -290 degrees Fahrenheit. Day and night, blistering and frigid, with nothing in between. And those days are incredibly long. Mercury rotates very slowly. One full rotation takes about 59 Earth days, and because of its orbital period and rotation rate, a single solar day on Mercury, from one sunrise to the next, lasts about 176 Earth days. You'd wait almost 6 months for the sun to go around the sky once. Think about that. Half a year of daylight, roasting. Half a year of night, freezing. But here's one of the genuinely weird things about Mercury: its density. Mercury is the second densest planet in the solar system, after Earth. And when you account for the compression of gravity, big planets get squeezed more by their own weight, which inflates their density. Mercury is actually the densest, pound for pound. It has a huge iron core, proportionally far larger than any other planets. The core makes up about 85% of Mercury's radius. Imagine a billiard ball. The hard inner part, the core, takes up most of the ball, with just a thin shell of rock around the outside. Something made Mercury iron-heavy, and the leading theory is that early in its history, Mercury was struck by a massive impact that blasted away much of its outer rocky mantle, leaving behind a planet that's mostly core. It's like a world that got skinned. And then there's something wonderful that the Messenger spacecraft discovered when it orbited Mercury from 2011 to 2015. Ice, water ice. On Mercury, the closest planet to the Sun, one of the hottest places in the inner solar system. How? Because Mercury's rotation axis is almost perfectly upright. It has virtually no axial tilt, which means that the floors of craters near the poles never see sunlight, ever. They're in permanent shadow, and in those shadows, where temperatures can drop below -300 degrees Fahrenheit, water ice has accumulated over billions of years, delivered by comets and asteroids, and it just sits there, frozen, in the eternal dark, while the sunlit surface a few miles away is hot enough to melt metal. It's one of those details that makes the solar system feel less like a textbook and more like a novel, strange, specific, and not at all what you'd expect. Now, let's move one orbit outward, to the second planet from the Sun. And if Mercury is a world of barren extremes, Venus is something else entirely. Venus is a nightmare, a beautiful, cloud-shrouded, hellish nightmare, and it's our closest planetary neighbor, almost exactly the same size as Earth, and it might be the most terrifying place in the inner solar system. Venus is sometimes called Earth's twin because of its size. It's about 95% of Earth's diameter and about 82% of its mass. If you saw Venus and Earth side by side, just as featureless spheres, you might have trouble telling them apart. But the resemblance ends at size. Venus's atmosphere is about 96% carbon dioxide, and it's thick, enormously thick. The atmospheric pressure at the surface of Venus is about 92 times the pressure at the surface of Earth. That's equivalent to being nearly a kilometer deep in Earth's oceans. And all that carbon dioxide creates a runaway greenhouse effect of staggering proportions. The surface temperature on Venus is about 864 degrees Fahrenheit, about 462 degrees Celsius, and it's remarkably uniform, day-side and night-side, poles and equator, all roughly the same blistering temperature. Venus is actually hotter than Mercury, even though Mercury is much closer to the Sun, because Venus's thick atmosphere traps heat so efficiently that the surface never gets a chance to cool down. It's an oven with the door locked shut. The surface of Venus is a landscape of volcanic plains, mountains, and craters, all viewed through that crushing, corrosive atmosphere. The clouds aren't water clouds. their sulfuric acid. The few spacecraft that have landed on Venus, all Soviet Venera missions in the 1970s and 1980s, survived for somewhere between 23 minutes and about 2 hours before being crushed, overheated, or corroded into silence. The images they sent back in those brief windows show a flat, rocky landscape under a dim, orange-tinted sky, with the thick atmosphere scattering light so thoroughly that there are no shadows. It looks like a world at permanent dusk. And here's a thought that planetary scientists find deeply unsettling. Venus might not have always been this way. There's evidence from modeling, from isotopic ratios, from the structure of the atmosphere, suggesting that Venus may have had liquid water on its surface in the deep past. Oceans, possibly. For maybe 2 billion years, Venus might have been a habitable world, not so different from Earth. And then something went wrong. The carbon dioxide built up, the greenhouse effect intensified, the oceans evaporated, the water vapor in the atmosphere enhanced the greenhouse warming further, and the whole system tipped over into the runaway state we see today. The water molecules were eventually broken apart by ultraviolet radiation high in the atmosphere. The hydrogen escaped to space, and Venus was left with this dense, dry, crushing blanket of CO2. The planet essentially cooked itself. And the reason scientists find this so unsettling is that it raises a question about our own world. Could it happen here? Probably not in the same way. Earth has plate tectonics and carbonate silicate weathering cycles that help regulate CO2. But Venus stands as a stark reminder of what a runaway greenhouse effect looks like when it reaches its conclusion. And then there's Earth, the third planet from the Sun, our planet. And honestly, the more you learn about the other planets, the more extraordinary Earth seems. Not because it's the center of anything, not because it's the biggest or the most dramatic, but because of the sheer improbability of the conditions that allow life. The liquid water, the breathable atmosphere, the magnetic field, the plate tectonics, the stabilizing moon, the protective Jupiter deflecting incoming debris. It's not that Earth was designed for life. It's that life evolved to fit exactly the conditions Earth happened to provide. And those conditions are maintained by an intricate web of geological, chemical, and astronomical processes that have been running for 4.5 billion years. Here's just one example that shows how interconnected everything is. Earth has a magnetic field, a strong one, generated by the churning of liquid iron in the planet's outer core, driven by convection and the planet's rotation. This is called the geodynamo. And that magnetic field extends far out into space, forming a bubble called the magnetosphere that deflects the solar wind, the stream of charged particles constantly flowing outward from the sun. Without the magnetosphere, the solar wind would gradually strip away Earth's atmosphere, the way it stripped away Mars's atmosphere when Mars's magnetic field died. And without the atmosphere, there's no greenhouse effect to keep the planet warm, no ozone layer to block ultraviolet radiation, no air to breathe. So the liquid iron core, churning away thousands of miles beneath your feet right now, is essentially a shield generator protecting the entire biosphere. Take it away, and Earth starts looking a lot more like Mars. And Mars, the fourth planet, the last of the rocky inner worlds. Mars is what makes this story so poignant, because Mars is the planet that almost made it. It's the planet that had liquid water on its surface, that had a thicker atmosphere, that had rivers and lakes and maybe even a shallow ocean in its northern hemisphere, billions of years ago, and then it lost it all. Mars is small, about half the diameter of Earth, about 1/10 the mass, and that smallness is probably what doomed it. Mars's smaller size meant that its interior cooled faster than Earth's. When the interior cooled, the liquid iron core solidified, And when the core solidified, the magnetic dynamo died. Without a magnetic field to protect it, Mars's atmosphere was gradually stripped away by the solar wind, molecule by molecule, over hundreds of millions of years. As the atmosphere thinned, the surface pressure dropped, and liquid water became impossible. At Mars's current surface pressure, water can't exist as a liquid, except briefly and under special conditions. It either freezes or boils. The rivers dried up, the lakes vanished. The planet became the cold, dry, rust-colored desert we see today, with an atmosphere that's about 1% as thick as Earth's, mostly carbon dioxide, and surface temperatures that average about -80 degrees Fahrenheit. But the evidence that Mars was once wet is everywhere. Orbital cameras have photographed ancient river valleys, carved by flowing water, branching and meandering across the landscape, exactly the way rivers do on Earth. There are layered sedimentary deposits in craters that look exactly like the kind of sediments that settle in lakes. There are mineral deposits, clays, sulfates, that only form in the presence of liquid water. The Curiosity rover, trundling around Gale Crater since 2012, has found evidence that the crater once held a long-lived lake, with water that was neither too acidic nor too alkaline, water that, by earthly standards, would have been drinkable. Mars was wet. Mars was warm enough. Mars might have been habitable. And if it was habitable, was it inhabited? That's the question that drives Mars exploration today, and it's the question that makes Mars, for my money, the most emotionally compelling planet in the solar system. It's the planet that shows you how thin the line is between a living world and a dead one. And you know what makes the exploration of Mars so compelling on a human level? It's that we've been watching it for so long. Mars has captured the human imagination more than any other planet. In 1877, the Italian astronomer Giovanni Schiaparelli observed what he described as canali on the Martian surface. The Italian word means channels, as in natural waterways. But when the word was translated into English, it became canals, implying artificial construction. The American astronomer Percival Lowell ran with this idea with passionate conviction, building an observatory in Flagstaff, Arizona, specifically to study Mars. He drew elaborate maps of the Martian canal network and wrote several popular books, arguing that the canals were an irrigation system built by an advanced civilization trying to survive on a dying, drying planet. It was beautiful science fiction masquerading as science, and the public loved it. H.G. Wells wrote The War of the Worlds in 1898, inspired partly by Lowell's ideas about a desperate Martian civilization. Edgar Rice Burroughs wrote his Barsoom novels. Ray Bradbury wrote The Martian Chronicles. Mars became the planet of our dreams, the place where we most wanted to find someone else out there in the universe. And then the spacecraft arrived, and the canals evaporated. Mariner 4 flew past Mars in July 1965 and sent back the first close-up photographs of the surface. They showed a cratered, barren, moon-like landscape with no canals, no vegetation, no signs of civilization. It was a crushing disappointment for the romantics. But the scientists quickly realized that Mars was fascinating on its own terms. Not because of fictional civilizations, but because of its real geology, its real history, its real potential as a place that once harbored the conditions for life. The disappointment of the canals gave way to the deeper, more profound excitement of looking for actual biology. And that search continues to this day. Now, beyond Mars, beyond the asteroid belt, that scattered ring of rocky and metallic debris between Mars and Jupiter, leftover material that never managed to coalesce into a planet because Jupiter's enormous gravity kept stirring things up. Beyond all that, the solar system changes character completely. You leave the zone of rock and metal and enter the realm of the giants. And the first giant you encounter, the king of the planets, is Jupiter. Jupiter is, in a word, enormous. It's the largest planet in the solar system by a wide margin, about 86,000 miles in diameter, more than 11 times the diameter of Earth. You could fit over 1,300 Earths inside Jupiter. It has more than twice the mass of all the other planets combined. If you could somehow pile Mercury, Venus, Earth, Mars, Saturn, Uranus, Neptune, and every moon and asteroid and comet in the solar system onto one side of a scale, Jupiter would still outweigh them all. It's a colossus. And Jupiter is made of almost entirely the same stuff as the Sun, hydrogen and helium, roughly the same proportions. If Jupiter had been about 75 to 80 times more massive, the pressure and temperature in its core would have been high enough to ignite nuclear fusion, and it would have become a star. A small, dim red dwarf star, but a star nonetheless. Our solar system would have been a binary star system, 2 suns in the sky. Jupiter fell short of that threshold, but it's about as large as a planet made of hydrogen can get. Here's a weird fact. If you added more mass to Jupiter, it wouldn't get much bigger. The additional gravity would compress the interior so much that the planet would actually get denser without getting much larger in diameter. Saturn, which is about 95 times Earth's mass, is almost the same diameter as Jupiter. Beyond a certain mass, gas giants stop growing outward and start growing inward. But the most immediately striking thing about Jupiter, the thing you notice the moment you look at it through even a small telescope, is the bands. Jupiter's visible surface, and I say visible surface in quotes, because Jupiter has no solid surface, no ground, just gas all the way down, getting progressively denser and hotter until hydrogen is compressed into a metallic liquid deep in the interior. Jupiter's visible cloud tops are organized into alternating bands of lighter and darker color. The lighter bands are called zones, the darker ones are called belts, and they're driven by Jupiter's incredibly fast rotation. Jupiter is huge, but it spins fast. One full rotation takes only about 9 hours and 56 minutes. That's the shortest day of any planet in the solar system. And that rapid spin, combined with the convective motions of the atmosphere, creates powerful jet streams at the boundaries between the bands, with winds that can reach 360 miles per hour. And then there's the Great Red Spot. You've probably seen pictures. It's a massive storm in Jupiter's southern hemisphere, an anticyclonic vortex, a giant high-pressure system that's been raging for at least 350 years, since astronomers first observed it in the 17th century. At its largest, the Great Red Spot was big enough to swallow 3 Earths side by side. It's been shrinking in recent decades. Observations show it was about twice as wide in the late 1800s as it is today, but it's still enormous, still churning, still that distinctive salmon-orange color that comes from complex organic molecules in the upper atmosphere being processed by ultraviolet sunlight. And Jupiter has moons, lots of moons. As of recent counts, Jupiter has well over 90 known moons. But the ones that matter most, the ones that changed the history of astronomy and are rewriting our understanding of where life might exist, are the 4 big ones. The Galilean moons, discovered by Galileo in January 1610, when he first turned his telescope toward Jupiter and saw 4 tiny points of light lined up near the planet, changing position from night to night. He was watching moons orbit another planet. It was the first direct proof that not everything in the universe orbits the Earth. It was a stake through the heart of the geocentric model. The 4 Galilean moons are Io, Europa, Ganymede, and Callisto, and each one is a world in its own right. each one fascinating in different ways. Io, the innermost, is the most volcanically active body in the solar system, more active than Earth, by a lot. Its surface is covered with hundreds of volcanoes, some of them shooting plumes of sulfur and sulfur dioxide hundreds of miles into space. The surface is constantly being resurfaced by lava flows. There are essentially no impact craters on Io because they get buried almost as fast as they form. The colors are stunning: yellows, oranges, reds, blacks, whites, a pizza-like palette that comes from various sulfur compounds at different temperatures. And what drives all this volcanism? Tidal heating. Io is caught in a gravitational tug-of-war between massive Jupiter and the other Galilean moons, particularly Europa and Ganymede. The orbital resonance between these moons keeps Io's orbit slightly eccentric, slightly non-circular, which means that the gravitational pull it feels from Jupiter varies as it orbits, squeezing and stretching the moon's interior like a stress ball being kneaded, generating enormous amounts of internal heat through friction. Io is being cooked from the inside, not by radioactive decay like Earth's interior, but by the relentless flexing of Jupiter's tidal gravity. And then there's Europa. If Io is fire, Europa is ice. Europa is slightly smaller than our moon, covered in a shell of water ice that is remarkably smooth. It's one of the smoothest surfaces in the solar system, with very few large craters, which means the surface is young and constantly being renewed. The ice is crisscrossed with a chaotic network of brown and reddish lines, cracks and ridges that form patterns eerily similar to the cracks in Arctic sea ice on Earth. And here's the thing that makes Europa one of the most exciting places in the entire solar system. Beneath that ice shell, there is almost certainly a global ocean of liquid water. Not a little lake, an ocean. Estimates suggest it might contain 2 to 3 times as much water as all the oceans on Earth combined. The evidence for this ocean comes from multiple sources. The Galileo spacecraft, which orbited Jupiter from 1995 to 2003, measured disruptions in Jupiter's magnetic field near Europa that are consistent with a salty, electrically conducting ocean beneath the ice. The surface features, the ridges, the chaos terrain, the patterns of cracking, are best explained by a frozen crust floating on a liquid layer that shifts and moves. And just like Io, the heat that keeps this ocean liquid comes from tidal forces. Europa's orbit is kept slightly eccentric by its resonance with Io and Ganymede, and the resulting tidal flexing generates enough heat to maintain liquid water beneath the ice. And where there's liquid water, there might be life. That's the tantalizing possibility. Europa's ocean is in contact with a rocky seafloor, which means there could be hydrothermal vents, hotspots where chemically rich water seeps up from the rock, similar to the hydrothermal vents at the bottom of Earth's oceans, which support entire ecosystems of organisms that live on chemical energy, not sunlight. Life around Europa's hypothetical hydrothermal vents wouldn't need sunlight at all. It would be completely independent of the sun, living in eternal darkness under miles of ice, powered by the chemistry of rock and water and the tidal energy of Jupiter. It's a staggering thought. And it's the reason that Europa is a top priority for future space missions. NASA's Europa Clipper mission, launched in 2024, is heading there to study the moon in unprecedented detail, looking for plumes of water erupting through the ice, mapping the ice shell's thickness, and searching for the chemical signatures of habitability. Now, let me say a bit more about why Europa is so exciting, because the science here is genuinely thrilling. On Earth, we have hydrothermal vents at the bottom of the ocean, places where seawater seeps down through cracks in the ocean floor, gets heated by volcanic activity beneath the crust, and erupts back out as superheated, mineral-rich fluid. These vents support entire ecosystems that run entirely on chemical energy, not sunlight. Giant tube worms, ghostly white crabs, dense mats of bacteria, shrimp with organs that can detect the faint infrared glow of the hot water. These organisms live in complete darkness, under crushing pressure, in water that would scald you, and they thrive. They get their energy from the chemistry of the vent fluid, from hydrogen sulfide and other chemicals, through a process called chemosynthesis, which is fundamentally different from the photosynthesis that powers most life on Earth's surface. The discovery of these deep-sea ecosystems in the late 1970s completely changed how biologists thought about where life could exist. Before that, it was assumed that life required sunlight. Photosynthesis was the base of the food chain. Period. But these vent communities proved that you could run an entire ecosystem on nothing but chemical energy and hot water. And that immediately made scientists look at Europa and think, wait a minute. If Europa has a liquid water ocean in contact with a rocky seafloor, and if tidal heating drives hydrothermal activity on that seafloor, then Europa might have the exact same conditions that support vent life on Earth. The water, the chemistry, the energy source, it's all potentially there, right now, under the ice, just waiting to be discovered. Ganymede, the third Galilean moon, is the largest moon in the entire solar system. It's bigger than the planet Mercury. It has its own magnetic field, the only moon known to have one, and it, too, is thought to have a subsurface ocean, sandwiched between layers of ice. Callisto, the outermost Galilean moon, is a heavily cratered ancient surface that's been battered for billions of years, and it may also have a subsurface ocean, though the evidence is less certain. Jupiter's system of moons is like a miniature solar system in its own right, a central body surrounded by orbiting worlds of startling diversity. And then there's Saturn. If Jupiter is the king, Saturn is the jewel. It's the second largest planet, about 72,000 miles in diameter, 9.5 times wider than Earth, and it is, by any measure, the most visually stunning object in the solar system. Because of the rings. Saturn's rings are one of those things that, no matter how many times you see them in photographs, no matter how much you know about them intellectually, will still take your breath away if you see them through a telescope for the first time. Galileo was the first to observe them, in 1610, but his telescope wasn't powerful enough to resolve them clearly. He thought Saturn had 2 large moons on either side, or perhaps ears. It wasn't until 1655 that the Dutch astronomer Christian Huygens, using a better telescope, correctly identified them as a flat ring encircling the planet but not touching it. And in 1675, the Italian-French astronomer Giovanni Cassini discovered a gap in the rings, the Cassini division, revealing that what had appeared to be a single ring was actually multiple rings, with spaces between them. And here's what's remarkable about the rings. They're enormous in extent. The main ring system stretches from about 4,000 miles above Saturn's cloud tops to about 50,000 miles out, spanning a diameter of roughly 170,000 miles. If you could drive across them at highway speed, it would take about 3.5 months. But they are astonishingly thin. The main rings are typically only about 30 feet thick, sometimes as thin as 10 feet. The ratio of width to thickness is like a sheet of paper the size of a football field. They're wafer thin, made up of billions upon billions of individual particles, chunks of ice mostly, ranging in size from tiny grains to boulders the size of houses, all orbiting Saturn independently, each one a tiny moon in its own right, all together, creating this vast, flat, shining sheet. Where did the rings come from? This is still debated. One leading theory is that they're the remnants of a moon or a comet that got too close to Saturn and was torn apart by tidal forces. The difference in gravitational pull between the near side and the far side of the object exceeded the object's own structural strength, and it was ripped to pieces. This limit, the distance within which tidal forces will destroy an orbiting body, is called the Roche limit, named after the French astronomer Édouard Roche, who worked out the math in 1848. Saturn's rings lie within, or near, Saturn's Roche limit. Another possibility is that the rings are relatively young, perhaps only 1 or 200 million years old, based on how bright and clean the ice particles appear, and were formed by a relatively recent disruption event, cosmically speaking. If that's true, then the rings are not a permanent feature. They're a temporary ornament, and we happen to live at the right time to see them. Dinosaurs might never have seen Saturn's rings, and billions of years from now, they may be gone. Saturn also has a stunning collection of moons. Over 140 known moons, including Titan, which is the second largest moon in the solar system and one of the most extraordinary worlds anywhere. Titan is the only moon with a thick atmosphere. Its atmosphere is denser than Earth's, about 50% thicker in terms of surface pressure, and it's composed mostly of nitrogen, just like Earth's. But the temperature on Titan is about minus 290 degrees Fahrenheit, far too cold for liquid water. And yet, Titan has something no other body in the solar system besides Earth is known to have: stable liquid on its surface, not water, liquid methane and ethane. The Cassini-Huygens mission, which arrived at Saturn in 2004, revealed that Titan has lakes and seas of liquid hydrocarbons, rivers that carve channels into the icy landscape, and a methane cycle that's eerily analogous to Earth's water cycle. Methane evaporates, forms clouds, rains down, collects in lakes, and evaporates again. It's like Earth in a funhouse mirror. Familiar processes, alien chemistry. The Huygens probe, which separated from the Cassini orbiter and parachuted down through Titan's thick orange haze in January 2005, was the first landing in the outer solar system. It sent back data for about 72 minutes after touchdown, and the images showed a landscape of rounded pebbles of water ice. Water ice is rock hard at Titan's temperatures, sitting on a surface that appeared damp, possibly with liquid methane. It was an alien shoreline, and the idea that Titan might harbor some exotic form of life that uses liquid methane as a solvent instead of water, is one of the most intriguing and speculative possibilities in astrobiology. And then there's Enceladus, a tiny moon of Saturn, only about 310 miles in diameter, that turned out to be one of the biggest surprises of the entire Cassini mission. In 2005, Cassini discovered that the south polar region of Enceladus was erupting. Enormous geysers of water vapor and ice particles were shooting out of fractures in the icy surface, fractures nicknamed tiger stripes because of their appearance, spraying material hundreds of miles into space. Some of this material actually feeds Saturn's E-ring, the faint outermost ring, and when Cassini flew through these plumes and analyzed the composition, it found water, sodium chloride, table salt, silica nanoparticles that indicate hot water interacting with rock, and simple organic molecules, all of which points to one thing: a subsurface ocean, kept liquid by tidal heating, with hydrothermal activity on the ocean floor. Enceladus, this tiny, overlooked moon, turned out to be spewing the contents of its hidden ocean into space, practically begging to be sampled. It's one of the best places in the solar system to search for extraterrestrial life, and it's only 300 miles across. I should also mention the Cassini mission in more detail, because it's one of the greatest space missions ever flown, and its story has a beautiful ending. Cassini launched in 1997, arrived at Saturn in 2004 and spent 13 years studying the planet, its rings, and its moons. During that time, it completed nearly 300 orbits of Saturn. It discovered 7 new moons. It found the geysers on Enceladus. It watched storms erupt on Saturn's surface and tracked their evolution over months. It measured the thickness and composition of the rings with extraordinary precision, finding that they're much younger than previously thought. And then, in September 2017, with its fuel nearly gone, Cassini was deliberately plunged into Saturn's atmosphere. This wasn't an accident. It was a carefully planned end-of-mission maneuver called the Grand Finale. The reason was to protect Enceladus and Titan. NASA knew that those moons might harbor conditions suitable for life, and they couldn't risk an uncontrolled spacecraft eventually crashing into one of them and potentially contaminating it with Earth microbes. So they chose to destroy Cassini in Saturn's atmosphere, where the heat and pressure would incinerate every trace of the spacecraft and any biological material it might carry. In its final hours, Cassini transmitted data continuously as it skimmed through the gap between Saturn and its innermost ring, then dove into the atmosphere. For about 91 seconds, it sent back direct measurements of Saturn's atmosphere, the first and only time a spacecraft has ever sampled Saturn's atmosphere directly. And then the signal went quiet. 20 years of mission, 13 years at Saturn, billions of miles traveled, and it ended with a final transmission from inside the clouds of the planet it had spent so long studying. There's something deeply poignant about that. A machine built by human hands, carrying human curiosity, sacrificing itself to protect the possibility of alien life on a tiny moon around a distant planet. If that's not a beautiful expression of what's best about our species, I don't know what is. And while we're talking about discoveries, let me tell you the story of how Uranus was found, because it's a lovely one. On the night of March 13, 1781, a musician and amateur astronomer named William Herschel was conducting a systematic survey of the sky from his garden in Bath, England, using a telescope he had built himself. Herschel was born Friedrich Wilhelm Herschel in Hanover, Germany, and had come to England as a young man to pursue a career in music. He was an accomplished oboist and organist, but he became obsessed with telescopes and astronomy, spending every spare moment grinding mirrors and observing the sky. His sister Caroline, who had followed him to England and worked as his assistant, was a remarkable astronomer in her own right. She would go on to discover 8 comets and become the first woman to be recognized with a salary for scientific work. On that night in 1781, Herschel noticed an object that didn't look like a star. Through his telescope, it appeared as a small, slightly fuzzy disk rather than a sharp point of light. His first thought was that it was a comet. He reported it as such. But as other astronomers tracked its motion over the following weeks and months, it became clear that the object wasn't following a cometary orbit. It was moving in a nearly circular path, far beyond Saturn. It was a new planet, the first planet discovered in recorded history, as all the others had been known since antiquity. Herschel wanted to name it Georgium Sidus, George's star, after King George III, who subsequently gave Herschel a royal stipend and the title of King's Astronomer. The French, understandably, were not enthusiastic about naming a planet after the British king. Eventually, the name Uranus was adopted, keeping with the tradition of naming planets after classical deities. Uranus, the ancient Greek god of the sky, father of the Titans, grandfather of Zeus. The discovery of Uranus doubled the known size of the solar system overnight. Saturn had been the outermost known planet for all of recorded human history, thousands of years. And suddenly, there was a new world beyond it, sitting quietly out there in the dark, twice as far from the sun as Saturn, so faint that no one had noticed it was a planet, despite the fact that, under ideal conditions, it's just barely visible to the naked eye. It had probably been observed before and catalogued as a faint star, but it took Herschel, with his superior telescope and his systematic, patient approach, to realize that it was something else entirely. The solar system was bigger than anyone had thought, and the implication was clear. There might be more out there. Now, beyond Saturn, the solar system becomes a colder, darker, more mysterious place. The two outermost planets, Uranus and Neptune, are often grouped together as the ice giants, distinct from the gas giants Jupiter and Saturn, because their interiors contain much more water, ammonia, and methane ice, relative to hydrogen and helium. They're smaller than Jupiter and Saturn, but still enormous compared to Earth. Uranus is about 4 times Earth's diameter, Neptune about 3.9 times. And we know remarkably little about them, because only one spacecraft has ever visited either one, Voyager 2, which flew past Uranus in January 1986, and Neptune in August 1989, on a grand tour trajectory that took advantage of a rare alignment of the outer planets that occurs roughly once every 175 years. Uranus is, frankly, the oddball of the solar system. It's tipped on its side. Most planets spin with their axes roughly perpendicular to their orbital plane. They spin like tops. Uranus's rotation axis is tilted about 98 degrees, so it's essentially rolling around its orbit on its side, like a ball rolling along the ground. The best explanation is that sometime early in its history, Uranus was struck by an Earth-sized or larger object that knocked it over. The consequences of this extreme tilt are bizarre. During Uranus's 84-year orbit around the Sun, each pole gets about 42 years of continuous sunlight, followed by 42 years of darkness. The seasons on Uranus are unlike anything else in the solar system. When Voyager 2 flew past Uranus in 1986, the planet appeared almost featureless, a smooth, pale blue-green ball with barely any visible cloud features, looking almost boring compared to the dramatic bands and storms of Jupiter and Saturn. But that appearance was partly due to a thick haze layer obscuring the atmosphere, and more recent observations from ground-based telescopes and the Hubble Space Telescope have revealed that Uranus does have storms and cloud bands. They're just hidden deeper down. The blue-green color comes from methane in the atmosphere, which absorbs red light and reflects blue-green. And Uranus has its own ring system, discovered in 1977, not by spacecraft, but by ground-based observers watching Uranus pass in front of a star. The star blinked on and off several times before and after being blocked by the planet itself, revealing a set of thin, dark rings around Uranus. They're much darker and narrower than Saturn's brilliant rings, made of very dark material that reflects almost no light. Uranus also has 27 known moons, many of them named after characters from Shakespeare and Alexander Pope, which gives Uranus's system a uniquely literary flavor. Titania, Oberon, Ariel, Miranda, Puck, Prospero, Caliban. Neptune, the 8th and outermost planet, is in some ways the most dynamic of the outer worlds, which is surprising given how far from the Sun it is, about 30 times Earth's distance, receiving only about 1/900th the sunlight that Earth gets. You'd expect a world that cold and that dimly lit to be sluggish, frozen, quiet, and yet, when Voyager 2 arrived at Neptune in August 1989, it found the fastest winds in the solar system. Sustained winds of over 1,200 miles per hour, more than twice the speed of the most powerful jet streams on Jupiter. Nobody fully understands why Neptune's atmosphere is so energetic. The planet radiates about 2.5 times more energy than it receives from the Sun, suggesting that its interior is still hot and actively driving atmospheric dynamics, but the exact mechanism remains a mystery. Voyager 2 also discovered Neptune's Great Dark Spot, a storm system reminiscent of Jupiter's Great Red Spot, though it turned out to be more ephemeral. When the Hubble Space Telescope looked for it a few years later, it had vanished, and a new dark spot had appeared elsewhere. Neptune's storms come and go, unlike Jupiter's centuries-old tempest. And Neptune has Triton. Triton is Neptune's largest moon, and it is almost certainly a captured Kuiper Belt object, a world from the outer solar system that Neptune grabbed gravitationally at some point in the distant past. The evidence for capture is that Triton orbits Neptune backwards, in the opposite direction from Neptune's rotation, which is called a retrograde orbit. No moon that formed in place around its parent planet should orbit backwards. Triton was something else before it was Neptune's moon, and the capture process must have been violent, involving enormous tidal interactions that would have heated Triton's interior and reshaped its surface. Triton's surface, as revealed by Voyager 2, is astonishing. It has a bizarre cantaloupe terrain, irregular, dimpled patterns that look like the skin of a cantaloupe melon, found nowhere else in the solar system. It has nitrogen geysers, the second body in the outer solar system found to have active eruptions, after Io, that shoot dark plumes of nitrogen gas and dust several miles into its extremely thin atmosphere. And the surface temperature is about minus 391 degrees Fahrenheit, making Triton one of the coldest known surfaces in the solar system. Despite that cold, there are hints that Triton might have a subsurface ocean. The tidal heating from its capture and its current orbital interactions with Neptune may have been enough to maintain liquid water beneath its icy crust. Yet another potential ocean world in a solar system that's turning out to be surprisingly wet. And beyond Neptune? Beyond Neptune, the solar system doesn't end. It keeps going, but the nature of it changes. You enter the Kuiper Belt, a vast ring of icy bodies orbiting the Sun beyond Neptune's orbit, extending from roughly 30 astronomical units to about 50 astronomical units from the Sun. An astronomical unit, by the way, is the average distance from Earth to the Sun, about 93 million miles. So the Kuiper Belt starts at about 2.8 billion miles from the Sun and extends to about 4.6 billion miles out. It's thought to contain hundreds of thousands of objects larger than 60 miles across, and probably trillions of smaller ones. And the most famous resident of the Kuiper Belt, the one that caused one of the great astronomical controversies of the 21st century, is Pluto. Discovered in 1930 by Clyde Tombaugh, a young astronomer at Lowell Observatory in Flagstaff, Arizona, Pluto was immediately classified as the 9th planet. Tombaugh found it through an incredibly painstaking process, comparing photographic plates of the same region of sky taken on different nights, looking for anything that had moved. It took months of tedious work, blinking back and forth between images, and finally, on February 18, 1930, he spotted it. A tiny dot that had shifted position, the 9th planet. For 76 years, Pluto held that status. And then, in 2006, the International Astronomical Union voted to reclassify it as a dwarf planet, and the solar system officially went from 9 planets to 8. The controversy was enormous, far bigger than the IAU probably anticipated. People were genuinely upset. There were protests, bumper stickers. New Mexico's state legislature passed a resolution declaring that Pluto was still a planet within their state borders, which is wonderful. But the scientific reasoning was sound, even if the public relations were bumpy. The issue was that astronomers had been discovering more and more Kuiper Belt objects of similar size to Pluto, in particular, a body called Eris, discovered in 2005 by Mike Brown and his team at Caltech, which is actually slightly more massive than Pluto. If Pluto was a planet, then Eris had to be a planet too, and so did several other Kuiper Belt objects. The choice was either to add a bunch of new planets to the list, with more likely coming every few years, or to establish a clear definition of what a planet is and apply it consistently. The IAU chose the latter, and the definition they settled on required that a planet must have cleared its orbital neighborhood, meaning it must be gravitationally dominant in its orbit, having swept up or expelled all the other objects near it. Pluto hasn't done this. It shares the Kuiper Belt with thousands of similar icy bodies. So it became a dwarf planet, the most famous member of a new category. And then, in 2015, the New Horizons spacecraft flew past Pluto after a 9.5-year journey from Earth, and what it found silenced a lot of the remaining debate, not about the classification, but about whether Pluto was interesting enough to deserve all the attention. It was. Pluto turned out to be far more complex and geologically active than anyone had expected. The most striking feature was a vast, heart-shaped region of nitrogen ice that the team informally named Tombaugh Regio, after Pluto's discoverer. Part of that heart, a basin called Sputnik Planitia, is a 1,000-kilometer-wide plain of nitrogen ice that appears incredibly smooth and young, with no impact craters visible, divided into polygonal cells that are slowly overturning in a process of convection, like a lava lamp in slow motion. There are mountains of water ice. Water ice is as hard as rock at Pluto's temperatures, towering miles above the nitrogen ice plains. There are hazy layers in Pluto's thin nitrogen atmosphere, illuminated by the distant sun, that create an ethereal blue glow. And Pluto's largest moon, Charon, has its own geological story. A reddish polar cap made of tholins, organic compounds processed by ultraviolet light, and a massive canyon system that dwarfs the Grand Canyon. Nobody expected any of this. When New Horizons launched in 2006, most scientists expected Pluto to be a cold, dead, cratered ice ball. Instead, it's a world with ongoing geological activity, atmospheric dynamics, and a beauty that the photographs captured with heartbreaking clarity. It was a reminder that the solar system is full of surprises, that distance from the sun doesn't mean distance from wonder. And the solar system extends further still, beyond the Kuiper Belt, in the hypothesized region called the Oort cloud. Trillions of icy bodies may orbit the sun at distances of up to 1 or even 2 light-years away, nearly halfway to the nearest star. We've never directly observed the Oort cloud, but its existence is inferred from the orbits of long-period comets, comets that plunge into the inner solar system on wildly elongated orbits that take thousands or millions of years to complete. These comets come from all directions, not just from the plane of the solar system, which suggests a spherical shell of icy bodies surrounding the sun at vast distances. The Oort cloud, if it exists, represents the true outer boundary of the sun's gravitational influence, the edge of where the sun can claim ownership, the place where our star's gravity finally fades to nothing and interstellar space begins. And speaking of comets, they deserve a moment because they're some of the most beautiful and scientifically important objects in the solar system. Comets are essentially dirty snowballs, or, as some scientists prefer, icy dirt balls, chunks of ice, dust, and rock, typically a few miles across, left over from the formation of the solar system 4.5 billion years ago. They've been preserved in the deep freeze of the outer solar system, essentially unchanged since the solar system's earliest days, which makes them time capsules. When a comet's orbit brings it close to the Sun, the ice begins to sublimate, to transition directly from solid to gas, creating the spectacular tail that has awed and terrified humans throughout history. The tail always points away from the Sun, pushed by the solar wind and radiation pressure, which means a comet's tail actually leads the comet as it moves away from the Sun on the outbound leg of its orbit. There are actually two tails, a dust tail, which is broad and curved, and an ion tail, which is narrow and straight, glowing blue from ionized gas. Ancient civilizations saw comets as omens, harbingers of change, signs from the gods. We now know they're just leftovers from the construction of the solar system, taking one last spectacular bow before retreating to the dark. The European Space Agency's Rosetta mission, which rendezvoused with Comet 67P/Churyumov-Gerasimenko in 2014 and dropped a lander named Philae onto its surface, revealed a comet up close for the first time. The comet was shaped like a rubber duck, two lobes connected by a narrow neck, with a surface of dark, rugged terrain, cliffs, boulders, and smooth, dusty plains. It was blacker than coal, absorbing most of the sunlight that hit it. And as it approached the Sun, jets of gas and dust erupted from the surface, creating an ever-changing coma and tail. The data from Rosetta and Philae included measurements of the comet's water, specifically the ratio of deuterium to hydrogen, which can serve as a fingerprint of where the water came from. Comet 67P's ratio was about 3 times higher than Earth's ocean water, which suggested that comets of this type were probably not the primary source of Earth's water. The search continues. I want to circle back to something we touched on earlier, the idea that the solar system is not just a collection of objects, but a system, a set of interconnected parts that influence each other in ways that are still being discovered. Jupiter, for instance, is sometimes called Earth's big brother, or Earth's guardian, and here's why. Jupiter's enormous gravity acts like a gravitational broom, sweeping up or deflecting many of the asteroids and comets that might otherwise drift into the inner solar system and threaten Earth. Computer simulations have shown that without Jupiter, the rate of large impacts on Earth would be significantly higher, perhaps up to 1,000 times higher, though the exact numbers are debated. The great extinctions in Earth's history, including the asteroid impact 66 million years ago that wiped out the non-avian dinosaurs, might have been even more frequent without Jupiter's protective gravitational influence. But it's more complicated than that. Jupiter doesn't just deflect things away from Earth. Its gravity can also redirect objects toward Earth. And the formation of Jupiter may have disrupted the inner solar system in the early days, scattering planetesimals and possibly even causing the late heavy bombardment, a period about 4 billion years ago when the inner planets were pummeled by a sharp increase in asteroid and comet impacts. So Jupiter is both guardian and troublemaker. It's a complex gravitational player in a complex gravitational game, and the orbits of the planets themselves interact in subtle ways over long timescales. This is the field of orbital mechanics, and it reveals something both beautiful and unsettling. The solar system is chaotic. Not in the everyday sense of the word. The planets don't fly off randomly, but in the mathematical sense, where tiny differences in initial conditions can lead to vastly different outcomes over millions or billions of years. The French mathematician Henri Poincaré showed in the late 1800s that the gravitational interactions of 3 or more bodies can't be solved exactly. There's no tidy formula that tells you where everything will be in the far future. You can only simulate it numerically, step by step. And those simulations show that over timescales of billions of years, the inner solar system is mildly chaotic. There's a small but real chance that Mercury's orbit could become unstable enough to cross the orbit of Venus, potentially leading to a planetary collision. It's an extremely unlikely scenario. The probability is maybe 1% over the remaining lifetime of the Sun, but the fact that it's not zero is a humbling reminder that the solar system's clockwork isn't quite as reliable as Newton made it seem. It's more like a clock that keeps excellent time for millions of years, but might skip a beat, very occasionally, in ways that are genuinely unpredictable. Let me paint you a picture of scale, because the distances in the solar system are genuinely difficult to grasp, and they're important for understanding just how empty and how vast this neighborhood of ours really is. We said the Earth is about 93 million miles from the Sun, 1 astronomical unit. Light covers that distance in about 8 minutes. Mars, at its closest to Earth, is still about 34 million miles away. Jupiter orbits at about 5 astronomical units, 5 times Earth's distance from the Sun. Saturn is at about 9.5, Neptune is at 30, and Pluto, way out in the Kuiper Belt, averages about 39.5 astronomical units from the Sun, roughly 3.7 billion miles. Here's a way to make those distances feel real. Imagine you shrink the Sun down to the size of a basketball. On that scale, the Earth would be a small bead, about 2 millimeters across, sitting about 26 meters away from the basketball. That's roughly the length of a swimming pool. Mars would be an even smaller bead, about 40 meters away. Jupiter would be about the size of a marble, sitting 135 meters away, more than a city block from the basketball. Saturn would be about 250 meters out. Neptune would be about 800 meters away, roughly half a mile. And Pluto? About 1 kilometer away from the basketball. And the nearest star, Proxima Centauri? On this scale, it would be another basketball sitting about 6,900 kilometers away, roughly the distance from London to New York. That's how empty space is. That's how alone the Sun is in its corner of the galaxy. When you look up at the stars, you're looking across gulfs of emptiness, so profound that the numbers almost lose their meaning. And here's the thing that makes the exploration of the solar system so remarkable. We've sent machines across those distances. Not quickly. It takes months to reach Mars, years to reach Jupiter, over a decade to reach Pluto. But we've done it. We've driven robots across the surface of Mars. We've dropped probes into Jupiter's atmosphere and Saturn's atmosphere. We've landed on a comet. We've sent spacecraft beyond the boundary of the solar wind, into interstellar space, where they're still talking to us, still sending data, still exploring, after nearly 50 years. The distances are vast, and we crossed them anyway, with math and physics and engineering and patience and curiosity. That's not a bad species to belong to. Now, here's something worth thinking about as we start to wind down. The solar system, as we understand it today, is not a static place. It's not a finished product. It's evolving, changing, and, on long enough timescales, it's temporary. The Sun is slowly getting brighter, about 1% more luminous every 100 million years. Over the past 4.5 billion years, the Sun has brightened by about 30% since it first ignited. In about 1 to 2 billion years, depending on the details of the models, the Sun will be bright enough that the additional energy will trigger a runaway greenhouse effect on Earth, evaporating the oceans and ending life on the surface. In about 5 billion years, the Sun will exhaust the hydrogen fuel in its core and begin to evolve off the main sequence. The core will contract and heat up. The outer layers will expand enormously. The sun will become a red giant, swelling until it's about 200 times its current diameter. Mercury will be engulfed. Venus will be engulfed. Whether the expanding sun will actually reach Earth's orbit is debated. The sun will also lose mass as it expands, which will cause the planet's orbits to migrate outward. But even if Earth isn't physically swallowed, it will be scorched into a molten, uninhabitable rock, its oceans and atmosphere long gone. After the red giant phase, the sun will shed its outer layers as a beautiful, expanding shell of glowing gas called a planetary nebula, a misleading name because it has nothing to do with planets. The name comes from the fact that early telescopes made these nebulae look vaguely planet-shaped. The core left behind will be a white dwarf, an incredibly dense remnant about the size of Earth, but with about half the sun's mass, a teaspoon of which would weigh several tons. The white dwarf will be searingly hot at first, but with no fuel source left, it will gradually cool over trillions of years, fading from white to yellow to red to brown, eventually becoming a cold, dark cinder in the void. A black dwarf. Though the universe isn't old enough for any white dwarfs to have cooled that far yet. It takes longer than the current age of the universe. It's the destiny that awaits our star. But that's all billions of years from now. Right now, in this particular moment in cosmic history, the solar system is in a kind of sweet spot. The sun is stable and middle-aged, burning its hydrogen fuel at a steady rate. Earth is warm enough for liquid water, but not so warm that the oceans boil. The planets are settled into their orbits, mostly well-behaved, their gravitational interactions nudging and tugging, but not destabilizing. The asteroid belt contains remnants that tell us about the system's construction. The comets preserve ice from its earliest days. The moons of the outer planets hide oceans that might, just possibly, harbor life. And we're here, living on a smallish, rocky planet, orbiting an ordinary middle-aged star, in the suburbs of an ordinary spiral galaxy, in a universe of 2 trillion galaxies, each containing hundreds of billions of stars, many of which probably have planetary systems of their own. The Kepler Space Telescope and its successor, TESS, have confirmed thousands of exoplanets, planets orbiting other stars, and the statistics suggest that, on average, every star in the Milky Way has at least one planet. That means there are more planets in our galaxy alone than there are grains of sand on all the beaches on Earth. And some of those planets are in the habitable zone of their stars, the right distance for liquid water to exist on their surfaces. We can't yet tell if any of them harbor life. The James Webb Space Telescope is beginning to analyze the atmospheres of some of these exoplanets, looking for biosignatures, chemical fingerprints that might indicate biological activity. We might get an answer within our lifetimes, or we might not. But the search itself is extraordinary. The fact that we can do it at all, that an ape on a small rock around a medium star can build instruments precise enough to detect the composition of an atmosphere 100 light-years away, that says something about what's possible when 4.5 billion years of evolution meets curiosity and mathematics. And maybe that's the best note to settle into sleep on. Not the vastness of the solar system, though it is vast, not the violence of its history, though it is violent, but the remarkable, improbable, deeply fortunate fact that there is a place in this solar system, this particular solar system, around this particular star, where the temperature is right, and the chemistry is right, and the conditions are right for molecules to organize themselves into something that can look up at the sky and wonder about what it sees. That's you, lying there, breathing, your body made of atoms that were forged in the cores of stars that died before the sun was born. atoms that drifted through space as gas and dust, that were pulled together by gravity into a spinning disk, that accreted into a rocky planet, that were rearranged by chemistry and time into something alive, something that can hear about the solar system and feel a little bit of wonder at how extraordinary it all is. The planets are out there right now. Mercury, baking and freezing in its slow rotation. Venus, shrouded in its crushing blanket of cloud. Mars, cold and red and still keeping its ancient secrets. Jupiter, with its swirling storms and its hidden moons full of water. Saturn, wearing its impossible rings like a crown. Uranus, tilted and mysterious. Neptune, lashing its atmosphere with supersonic winds. And all of them, every single one, orbiting the same star that will rise over your horizon in a few hours. The same star that warmed the face of every human who ever lived. The same star that has about 5 billion good years left in it. You're part of this system. You're made of its materials, shaped by its conditions, warmed by its star, held in place by its gravity. And every time you look up at the night sky, at the moon, at the bright dot of Venus low on the horizon, at the reddish speck of Mars, you're looking at family. Distant, strange, inhospitable family, maybe. But family, born from the same cloud, shaped by the same forces, orbiting the same ancient fire. So let the solar system turn. Let the planets trace their quiet ellipses. Let the comets fall, and the moons hold their oceans, and the rings shimmer in the sunlight that takes an hour and 20 minutes to reach them. It's all happening right now, all of it, and it doesn't need you to stay awake for it. It'll still be there in the morning. The whole beautiful, improbable, 4.5 billion-year-old machine, ticking along, keeping time in the dark. Let your breathing slow. Let the numbers and the names and the stories settle somewhere soft, and let the same gravity that holds the planets in their orbits hold you gently, right where you are, on this warm and watered rock, the third one out from the sun, turning slowly toward morning.